Hello, my name is Manuel Combarro and I will present you our work submitted to the CP2023 conference, which is titled Constraint Model for the Satellite Image Mosaic Selection Problem. In recent years, the Earth observation industry has experienced a rapid growth. To illustrate the magnitude of this growth, consider the number of satellites observing the Earth in 2021 exceeded 4 times the count in 2014. And the amount of satellite imagery produced per day was bigger than 100 terabytes. This surge in available imagery has led to the creation of numerous applications, included but not limited to crop monitoring, natural disaster management, and environmental monitoring. In many cases, these applications need to study a large area of interest, which cannot be covered by only one image, as can be seen here. In order to cover the whole area, it is necessary to merge several images together into a big single one image. This final image is called a mosaic. Generating a mosaic is a challenging task because you need to merge several images that were taken from with different illumination conditions and from different angles. But in this work, we focus in a challenge, in a problem that appears before producing the mosaic, and it is which images should be considered to build the whole mosaic. Let's look at an example to better understand this problem. Here the satellite images has been colored for a better visualization. In this scenario, you have 30 images covering the area of interest, and you need to determine which one are going to be selected to build the mosaic. A trivial solution to this problem would be to build a mosaic with all the 30 images. However, if you want to optimize the number of images, this approach is far from ideal. As we can see here, with only 4 images, we can't cover the whole area of interest. So we only need these 4 images to build a mosaic. This problem can be seen as an extension of the NP-hard problem of finding the cover of a polygon without holes, a rectilinear polygon without holes with axis parallel rectangles. Here in our problem, the axis parallel rectangles are the images and the rectilinear polygon is the area of interest. We say that this is an extension of the previously mentioned covering problem because in our case the covering shapes are not always rectangles and are not always axis parallel. Furthermore, we consider more than one objective, specifically these 4 popular parameters of satellite images: the cost of the image, the cloud coverage of the image, the resolution of the image, which indicates how many square centimeters represents 1 pixel of the image in the Earth, and the incidence angle, which is related to the image's capture angle. In general, in this multi-objective problem, there might not be any one objective more important than the others. So to solve this problem, we have to generate the Pareto front and let the user to choose the preferred solution. We have to highlight that a unique aspect of this problem is the minimization of the cloudy areas of the cloud coverage. In contrast to other objectives, the cloud coverage does not have the same value throughout the image. For example, the resolution of the image is the same in the corners of the image or in the center of the image. But not all the images have the same amount of clouds, as you can see here, except if the image has a 0% or 100% of cloud coverage. Due to this particularity, it is possible to reduce the number of clouds in the final mosaic if we can find a combination of images that can overlap the cloudy regions of the other images, as can be seen here. To the best of our knowledge, there is no existing work that applies this modeling or this technique to reduce the amount of clouds in the final mosaic. To tackle this problem, we propose a constraint model and a mixed integer programming model. However, we don't directly model the original problem, but a transformation. we have to make this transformation to the geometric characteristics of the problem, as it is difficult to encode operations like polygon intersection and polygon union. With this transformation, we remove these geometric characteristics of the problem. In order to do the transformation, we need to apply two preprocessing steps. Before explaining these steps, we have to mention that we only consider the parts of the images that are inside the area of interest, this part here, because the part of the images that are outside the area of interest doesn't affect the cover. Having mentioned that, let's explain the first preprocessing step. First, with the GEOS library, we find all the polygons that are formed by the intersection of the edges of the images. These polygons or parts do not overlap, and their union is equal to the whole area of interest, to the universe. With this, also for each polygon or part, we know which images can contain that part, that polygon. With this, we can model the cover constraint and the cost constraint as the weighted set cover problem, where the universe is the union of all these polygons or parts, and the images are the sets, and the weight of the image is the cost of the image. The second preprocessing step is to detect the clouds of the images and add them to the universe and to the corresponding sets. The objective of doing this is to know whether a region of the mosaic represented by an element of the universe is free of clouds. We consider that an element or part is the same, is free of clouds if there is at least one image in the cover that contains that element and does not have clouds in that region. In real applications, cloud can be detected using cloud detectors, but as this is an orthogonal problem to our research, we do not detect the clouds, but we randomly assign them, allocate them inside the image, setting one part or several parts completely cloudy. How we do this? We know we have metadata of images indicating the cloud coverage of the image. We assume that the cloud coverage percentage of the image inside the area of interest is equal to the total cloud coverage percentage of the whole image. And with this number, we start to randomly allocate the clouds inside the images by setting a part completely cloudy until we reach this cloud coverage number. In real cases, it could be that most of the clouds are outside the area of interest. If you have that, then inside the area of interest, the cloud coverage percentage is much less than the whole cloud coverage percentage of like the cloud coverage percentage of the whole image. This doesn't happen if we apply this random allocation method. We also have to highlight that in real cases, it is possible that the clouds don't fully cover a part. In this case, at least two parts are created, one representing the area without clouds and the other one representing the cloudy area. Here, we can see an example of this situation where in the intersecting region, we have two clouds from the two images, and these clouds do not fully cover the intersecting region. As a result, instead of having only one element, we have three. One for each cloud and another one for the non-cloudy region for the non-cloudy part of this region. Now let's see the CP model for this problem. First, we have the covering constraint that indicates that the union of the images that belongs to a cover T must be equal to the universe. And then we have let's see how we model each one of the objective. First, the cost is equal to the sum of the cost of the images to belong to the cover. These two constraints, the covering constraint and the cost constraint, are identical to the weighted subcover constraints. The incidence angle, the constraint that represents the incidence angle, is this one, and the incidence angle is equal to the maximum incidence angle of the images in a cover. The resolution is equal to the sum of the resolution of each part. The resolution of a part is equal to the minimum resolution of the images that contain that part and are in a cover. Finally, the cloud coverage is calculated as the sum of the area of the clouds that are not covered by other images. For each part, we have a set of images that contain an uncloudy view of the part, and if none of these images are selected in a cover, then that part is cloudy. Okay, in addressing this multi-objective problem, a key aspect is the strategy for generating the Pareto front. We have employed two distinct strategies capable of finding the exact Pareto front if given sufficient time. For the constraint model, we employ Gabanelli's approach. This strategy consists in running a satisfaction constraint solver iteratively. In each iteration, we make sure that at least one of the objectives is improved compared to the previous iteration. For instance, imagine a problem where we aim to maximize two objectives, x and y, and we have in dissatisfaction, x equal 10 and y equal 5. Then we add this constraint, x greater than 10 or y greater than 5. With this, we guarantee that in the next iteration, one of the two objectives is going to be better than in the previous one, the x or the y. After we get a solution for this satisfiability problem, we need to check if the solution belongs to the front or not. We continue doing this process until the model becomes unsatisfiable. When this happens, we can guarantee that all the points belonging to the exact Pareto front has been found. Okay. In contrast, for the MILP approach, we employ a different strategy, the sum-and-con method. This approach is a faster implementation of the classical epsilon constraint idea, as it bypasses unnecessary optimization steps, resulting in a reduced number of iterations. In the epsilon method, one specific objective is optimized while the others are converted into constraints. With the constraint objective, we build a grid. Where each dimension of the grid corresponds to the range of possible values of the objectives. The epsilon constraint method explores all the points in the grid to find the exact Pareto front. The sum-and-con method implements several mechanisms to skip the unnecessary exploration of points in the grid. For example, if at some point the problem is unfeasible, it is useful to tighten the constraint, as the resulting model is going to be also infeasible. Let's see an example of this method. Suppose you want to maximize three objectives, x, y, and z, being y and z the constraint objective, and with minimum values of 5 and 10 respectively. In the first iteration, we add this following constraint, y greater or equal than 5. We optimize. Then when we got the solution, we add the following constraint, y greater or equal than 6. We repeat this until the model becomes infeasible, or y is greater, or we have to apply this constraint, y greater or equal than y max plus 1. Then when we reach this point, we restart the y constraint. We set y greater or equal than 5, but for z we tied the constraint for z. We said that z has to be greater or equal than the z previous value plus 1. And for example, like this, y will be greater or equal than 5 and z greater or equal than 11. We stop when all the possible values of the grid of this grid has been explored, from y min to y max and from z min to z max. We have to mention that all the optimizations steps in this method produce solutions that belong to the exact Pareto front, as opposite of the Cabanelli's strategy. To evaluate the proposed models, we perform experiments considering 5 areas of interest in the world: Mexico, Rio de Janeiro, Paris, Lagos, and Tokyo. We use metadata of real images that were captured between January of 2021 to January of 2023 by the satellite constellations Spot and Pleiad. For each area, we simulate 5 scenarios where the number of images goes from 30 to 200, except for Lagos, where the maximum number of available images in that time, during that period of time, was 145. We solve each instance using the CP and MILP models. For the CP model, we solve it using the ORTools solver and the G-code solver, and for the MILP model, we used the Gurobi solver. The running time for each instance was 1 hour, and regarding to this, we have to mention that for CP solvers we use min-sync, and not all the running time was used to get the Pareto front, as part of the time is used by min-sync to flattening the model. To compare the resulting fronts, we use the well-known metric hypervolume. Now let's discuss the experimental results. As mentioned before, to compare the results, we use the hypervolume of the Pareto front. For each instance, we score the strategies, calculating how worse they were compared to the best. For example, a score of 1 means that the strategy has the same hypervolume that the best strategy for that instance, and a score of 0.5 means that the hypervolume of the strategy is half of the best hypervolume for that instance. For only one instance, the complete Pareto front was found in the running time. The solvers that found the complete front were ORTools with the default and greedy search and Gurobi. For the rest of the instances, the whole Pareto front was not found, and the hypervolume corresponds to the partial front obtained during the running time. Also, for 3 use cases, Paris, Rio, and Tokyo, with 200 images, the entire time was used by min-sync only to flatten the model. Despite of this, the best strategy, the strategy that obtained the best results was ORTools with the default search. In the left graph, we can see that ORTools with the default search got in 13 times of 24 the best hypervolume, and Gurobi and ORTools with greedy search perform more or less the same. In the right graph, the average score of each strategy is presented. We can see that ORTools with the default search had a score of almost 0.85, and here also, and we can see here that ORTools with the greedy search and Gurobi also had a similar performance. Also, we can highlight that G-code, independently of the search strategy used, was always the worst strategy, the worst approach. Considering the previous results, we can conclude the following. The CP model solved with ORTools solver using the default search obtained the best results. The proposed greedy search strategy could not outperform the default search strategies. of the constraint solver, but for G-code it produced very similar results. The CP model produced better Pareto fronts than the MILP model. This could be related to the method we use to generate the Pareto front, but we need to research further in this why this happened. And for future research, it will be interesting to compare different approaches to generate the exact Pareto front for the CP and MILP model based on the metric anytime behavior for the hypervolume. Also, it will be interesting to propose heuristics to tackle bigger instances and evaluate its performance against the proposed CP and MILP models. That was all. Thank you very much for your attention, and if you have any questions, you can reach us through these emails. Thanks again, and have a very nice day.